This video will investigate one of the key ideas of inferential statistics, the central limit theorem. The discussion will begin with the idea of sampling distributions. To understand sampling distributions, it is important to know the difference between a population and a sample. We will also discuss the importance of the size of the sample. Then we will apply the central limit theorem to an inferential statistics problem. Remember from Chapter 1 the definition of a population and the definition of a sample. A population is the entire set of items we are interested in. It could be individuals or some object of interest. We are then interested in some parameter of that population. It may be the mean or some measurement or the weight of some object or some other characteristic of each member of the population. A sample is a portion of the population. A sample is simply a subset of the population. To ensure accuracy, we strive to select random samples using various sampling techniques like stratified or systematic random sampling. A sampling distribution is the frequency distribution of a statistic from each member of the set of all possible subsets of a given size for a population. We call the size of the sample N. When we say all of the possible subsets, we mean exactly that, all possible subsets. That could certainly be in the thousands or even millions or more possible subsets. Let's look at an example where we have 10 people and want to estimate the average age of those people. This is a case where we could easily calculate the mean, but let's work on the problem through using estimation to see the process. We will take a sample of 2 and calculate the mean age for the 2 people in the sample. With a population of 10 and a sample size of 2, there are 45 possible samples. This can be calculated using combinations. We want the combination of 10 items taken 2 at a time. The formula is 10 factorial divided by 2 factorial times 10 minus 2 factorial. This gives us the possible pairs from the 10 people. Notice that 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 10 factorial can be written as 10 times 9 times 8 factorial. This makes factorial calculations much simpler. In our example, we have 45 possible subsets of size 2. If we take the frequency distribution of the mean of all 45 of those subsets, we have the sampling distribution. We will look at that closer in an upcoming video. But for now, suppose we look at a random sample of 2 and calculated the sample mean of 41. We understand that it is probably not exactly the mean of the population because of sampling error. but the sampling distribution can help us determine how close 41 is to the true mean of the population. What does the sampling distribution look like? We know it has 45 members, the combination of 10 items taken 2 at a time. In Excel, use the function equals COMBIN parentheses 10, comma 2, and that will calculate the combination. The central limit theorem can now be used to describe the sampling distribution. The central limit theorem tells us that if the underlying population is distributed normally, then the sampling distribution will be distributed normally. This is true regardless of the sample size. The central limit theorem also tells us that even if the population is not normal, the sampling distribution will tend toward being normal as the sample size increases. If the underlying population is fairly symmetrical, a sample size of 10 or more will result in a normal sampling distribution. However, if the population is heavily skewed or bimodal or any other shape, it will take a larger sample size to ensure a normally distributed sampling distribution. For any population distribution, a sample size of 30 or more will allow us to assume normality in the sampling distribution. The central limit theorem also tells us more about the sampling distribution. We know that the mean of the sampling distribution will be always the same as the mean of the population. If the sample size is greater than or equal to 30, the variance of the sampling distribution will be the variance of the population divided by the sample size. That leads to the standard deviation. The standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of the sample size. If the sample size is a significant portion of the population, 5% or more, the standard deviation of the sampling distribution must be adjusted using the finite population correction factor. This will be discussed in the next video. Our example uses a population of 10 and a sample size of 2. What if our population size is 10,000 and we have a sample size of 30? How many subsets will we have? The combination of 10,000 items taken 30 at a time is an easy calculation in Excel. The result is 3.60935 times 10 to the 87th power. That is an immense number. We could never find each value and build a frequency table. Fortunately, because we have the central limit theorem, we know a lot about the sampling distribution. First, we know it is normally distributed because the sample size is 30. We know that the mean is the same as the population mean, and we know that the standard deviation is the standard deviation of the population divided by the square root of 30. In the next video, we will look at this example. The first chart is ages of 10 individuals. We do not have a frequency distribution of the population in this slide, but the distribution has no real shape. The distribution of the sampling distribution when n equals 2 is beginning to take some shape. We will continue with this example in the next video. In summary, the central limit theorem tells us a sampling distribution will be normally distributed if the sample size is 30 or more. The mean of the sampling distribution is equal to the mean of the population. The standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of the sample size.